Today we are going to solve two problems, that is problem 2.8 and problem 2.9 of Griffith third edition introduction to quantum mechanics. The problem 2.8 is a particle of mass m in the infinite square well of with a start out in the state psi of x and 0 is equal to a in between 0 to a by 2, x is between 0 to a by 2, and it is 0 between a by 2 to a. So here to here it is 0, wave function is 0 at this range, it is wave function is 0. Here the wave function is a, so it's a constant. You have this, so we have to take because it's a constant, it's a fixed one, so it is not a eigenfunction of the Schrodinger wave equation because it's a constant. But how we can create this square like this, we have studied in the Fourier transformation technique that it is the linear combination of so many sinusoidal wave. So here the question is for some constant a, so it is at the time t equal to 0, equally like to be found at any point in the left half of the wall. So you can find at the left side. What is the probability that measurement of the energy at some later time would yield value pi squared h cross squared over 2ma squared? First, we will find the normalization constant. That is integral between minus infinite to plus infinite modulus psi squared dx must be equal to 1. Here, between 0 to a by 2, this wave function is a. So you can take a squared integral dx, which is equal to 1. So if you integrate dx, you will get x. So x, when you substitute the x a by 2, x is 0 0, so a by 2, if you substitute, this will become a squared a by 2 is equal to 1. That means a squared is equal to 2 over a, and a is equal to square root of 2 over a. And now we have to find the probability that a measurement of energy at some later time would yield the value pi squared h cross squared over 2ma squared. The energy value is pi squared h cross squared over 2ma squared. It is referred when n is equal to 1, because actually this is n squared pi squared h cross squared over 2ma squared. For infinite square well potential, where the nth state wave function is square root of 2 a sine n by a x psi 1. When n is equal to 1, you will get square root of 2 over a sine pi over a x. So this is the wave function. Remember that we got the wave function a. That is very important. So that is actually this is a linear combination of so many sinusoidal wave. That is like psi 1 of x. So we know this psi star is a at initial wave function. Psi 1 is equal to this one. So which is equal to the coefficient C1. Now we will carry out this integral. Now we got this expression. Now replace a by a value of a is square root of 2 over a. Now there is already one square root of 2 over a. So if you multiply both, you will get 2 over a. And this integral part is integral between 0 to a by 2 sine pi by a x dx. So now if you integrate this, you will get minus cos pi by a x over pi by a. So this pi by a in the denominator will become as a over pi. So now this a will get cancelled. Then you will get 2 over pi. If you apply the upper limit, minus cos, if you apply a by 2, x is a by 2, then this a and this a will get cancelled. You will get pi by 2 minus cos pi by 2. If you apply the lower limit, uh, cos 0 is 1. So naturally, it is already there is a minus sign. So minus of minus will become plus 1. So cos pi by 2 is 0. So naturally, this will become 2 over pi. So the probability is modulus square of C1. So which is equal to 2 over pi whole squared, which is equal to 4 over pi squared. So if you substitute the value of pi squared, then you will get the probability is 0.440 pi. Then we will move on to next problem. Now we will solve the problem 2.9. The problem 2.9 is for the wave function in example 2.2. Find the expectation value of Hamiltonian H at the time t equal to 0, the old-fashioned way. The Hamiltonian is expectation value of Hamiltonian is integral psi of x0 H cat psi of x0 tx. Compare the result we got in example 2.3. So first you find the normalization constant. For that, integral between 0 to a modulus psi squared tx must be equal to 1. So now psi is given from the example 2.2. This equation is from example 2.2. So you replace modulus psi squared by this wave function. So which is equal to a squared I am taking outside and x squared a minus x whole squared. If you expand and carry out this straightforward simple integration. So here you will get a squared is equal to 30 pi a power 5. Now we will continue further. First, we will find what will happen if Hamiltonian act on the wave function psi of x and 0. Already it is given psi of x and 0 is equal to uh, this one a x into a minus x. So you replace Hamiltonian by its operator, that is minus h cross square over 2m delta 2 over delta x2. Here we have taken potential, of course, for infinite square. Well, it is 0. So we have taken only the kinetic energy term. Since A is constant, I am taking out of the derivative. So now you bring this x inside the bracket, then you will get ax minus x squared. Now you take second order derivative. We take first order derivative, first term will become just a, second term minus 2x. If you take the second derivative, a will be 0, constant. If you differentiate constant, it will be 0. Then this will become just minus 2. That's what I have given. Here you know minus h cross squared over 2m into a. So minus of minus will become plus, and this 2 will get cancelled. So you will get h cross squared over m multiplied by a. Then what is the expectation value of the Hamiltonian? The wave function x multiplied by a minus x, and of course the normally the that is a capital A and h this one. So we have seen h is equal to this h uh, act on psi. Sorry, h act on psi. When h act on psi, what will happen? you will get h cross square over m, and already there is one a here, one a, it will become a squared h cross squared over m, and you differentiate this, sorry, integrate x into a minus x dx. As usual, you bring x inside the integral, you will get like this, ax minus x squared. Now we got this expression. We have to carry out this integration. So here you have a squared h cross squared over m, and this will be, if you integrate this, x will become x squared over 2, and this is x cube over 2, between the limit 0 to a. So first term will become squared is a squared, a cube over 2, and this is also a cube over 3. Uh, if you apply lower limit, it will be 0 naturally. So you take LCM 6. So 3a cube minus 2a cube. If you subtract this numerator, you will get simply, here you keep this a squared h cross squared over m as it is. Then this will be a cube over 6. Then you replace a squared. We have seen a squared is equal to uh, 30 over a5. Now you can cancel this a5 with this a3. So this will become a squared. Then this 6 with this 30, you will get 5. So you will get 5 h cross square over m a square. Exactly what you got the result from example 2.3. Thank you very much for watching my video and supporting me continuously. Thank you very much.